In our last video, we discussed gases in terms of their temperature, their volume, and their pressure. This time, we're going to add another variable, the amount of gas itself. Here we go. We know that gas particles can be different in terms of their size. Radon atoms are much larger than helium atoms, for example. However, the kinetic molecular theory tells us that despite that fact, those particles are so far apart that the size of each particle doesn't really have an influence on the overall volume of that gas. Amedeo Avogadro was the first one to really figure this out. He proposed that if you have two samples of a gas at equal temperature, equal volume, and equal pressure, that you'll have identical numbers of particles in those samples. We call this Avogadro's principle. Again, it doesn't matter which gases you're talking about. If you have samples of them at equal temperature, volume, and pressure, you will have identical amounts of particles. That's really something. Avogadro went one step further. He actually calculated how much volume 1 mole of any gas will occupy at standard temperature and pressure. Now, standard temperature, if you don't remember, is 0 degrees Celsius or 273 Kelvin. Standard pressure is 1 atmosphere. Turns out the molar volume of a gas is 22.4 liters. That is to say, 1 mole, any gas at standard temperature and pressure will have a volume of 22.4 liters. So if you have a gas at standard temperature and pressure, you can use that conversion factor to make calculations for volume or for moles. Let's say you have 5.6 liters of any gas. It's at standard temperature and pressure. So to compute how many moles you have, we simply divide by 22.4 liters. 5.6 divided by 22.4 gives us 0.25. That is 0.25 moles of gas at standard temperature and pressure. Incidentally, this allows us to finally travel that third leg of our Molopolis map, the journey from Molopolis to Leaderville. As you can see, we take Interstate 22.4 to get there. If you're converting from moles to liters of a gas, then you multiply by 22.4. If you're coming back from Leaderville to Molopolis, you divide by 22.4. Remember though, we have to be talking about standard temperature and pressure. In our last video, we said that you could take Boyle's law, Charles' law, and Gay-Lussac's law and bring them together to form the combined gas law, which gives us the relationship between pressure, volume, and temperature. Now here's the thing. For a specific sample of a gas, the relationship between pressure, volume, and temperature turns out to be a constant. So we could write it like this. Now, let's add one more variable to the mix, the amount of gas. What if it changes? Let's consider for a moment the inflation of a tire. When I inflate that tire, I'm adding more gas particles into the tire, right? What does that mean? More gas particles means more collisions with the container walls. That means more pressure. From that, we can say that the pressure of a gas and the amount of gas, or number of moles, is a direct relationship. The greater the number of moles, the greater the pressure. We can also see this with volume, right? The number of moles is directly proportional to the volume. Because of that, we can incorporate the number of moles, or a lowercase n, into our equation, like this. PV divided by NT equals a constant. Turns out, after many, many years of experiments, that constant has a numerical value. We call this the ideal gas constant, and we represent it with a capital R. If we're dealing with atmospheres of pressure, the value of R is 0.08206 liter atmospheres over moles Kelvin. As you can see, the units for R are simply a combination of the other four variables. The value of R may change depending on what units of pressure you're using. Much of the time we'll use atmospheres, and so it'll be the 0.08206. But if you happen to be using kilopascals instead, your R value will be 8.314 liter kilopascals over moles Kelvin. This may occur to you already, but just in case, 8.314 is 101.3 times 0.08206. Why is that? Because 1 atmosphere is equal to 101.3 kilopascals. You get it? So if the units of pressure change, no big deal. There's an R value for that. We can even change it for millimeters of mercury, or torr. The value of R then is 62.4 liter torr over moles Kelvin. And yes, that value is 760 times 0.08206 because 1 atmosphere is equal to 760 torr. Now, if we substitute R for that constant and rearrange it into an equation form, we get the ideal gas law. Pressure times volume equals the number of moles times the constant R times temperature, or just PV equals nRT. So if you have 3 out of your 4 variables, you can find the other one using the ideal gas law. Let's say we have a 0.323 mole sample of the gas. We're holding it at a temperature of -8 degrees Celsius, and the pressure is 0.9 atmospheres. The question is, what is the volume of that gas? So we're going to use PV equals nRT. We have pressure, we have the temperature, or do we? Remember, Kelvin, right? So let's go ahead and change this so that we have the correct temperature. There we go. We have our correct temperature, so now all we need is R. Which R do we use? Well, in this case, we're using atmospheres, so we'll use 0.08206 for our value of R. Now we have the variables that we need to find volume. To find volume, we'll rearrange the equation. nRT divided by P will give us volume. And now we simply fill in the values. Once we've plugged in our numbers, we do the math and we get a value of 7.80 liters. Here's the cool thing about the ideal gas law. We can rearrange it to solve for other things like molar mass or even density. Let's say we want to find the molar mass of a gas. In order to do that, we can use the ideal gas law, but we need the pressure, the volume, the temperature, and the mass of the sample. Here's how we do it. The number of moles, or N, is found by taking the mass of the sample and dividing it by the molar mass. Remember that? Going from Gramsberg to Molopolis, we divided the mass by the molar mass. We do the same thing here. So let's substitute mass over molar mass, or little m over double big M, into our equation. Now we have PV equals mass times RT divided by molar mass. When we rearrange, we can solve for the molar mass. The molar mass is equal to mass times RT divided by PV. There you go. We can solve for the molar mass of a gas sample using the ideal gas law. If you look closely, we can also solve for density. Notice in this equation we have mass on top and volume on bottom. Mass per unit volume is density. So if we substitute mass over volume with a D for density, we get molar mass is equal to density times RT divided by P. If we rearrange, we get density is equal to the molar mass times the pressure divided by R and temperature. So from one ideal gas law, we now have 2 other equations as well that are very useful to us. Let's talk for a moment about what we mean by ideal gas law. We're talking about a gas that observes the principles of the kinetic molecular theory. Their particles don't take up space. They don't exert any attractive or repulsive forces on each other. They're in constant random motion, and all of their collisions are elastic. Truth be told, no gas is perfectly ideal. I mean, gas particles do have volume, and they do experience attractive forces and repulsive forces. The collisions that they undergo are not always perfectly elastic. Here's the good thing though. Most gases will behave ideally in a wide range of temperatures and pressures. Now there are some occasions in which the ideal gas law doesn't work well for a real gas situation. For example, if we have high pressure, extreme pressure, think about what's happening there. That means that the particles themselves are being pushed together more closely, maybe even to the point where their actual size is no longer negligible. It may make a difference. I mean, a lot of people use propane gas for their grills, and propane will liquefy if enough pressure is applied. Obviously, liquid is not a gas. The other extreme would be very low temperature. If you have very low temperatures, that means the kinetic energy decreases in those gas particles, which means they slow down enough to where they might possibly interact with each other with intermolecular forces, causing them to liquefy. Again, no longer a gas. So, extreme high pressure, extreme low temperature, those are the conditions that we don't want to have when we're dealing with a real gas. Otherwise, we're not going to be able to use the ideal gas law. 2 other things that may make a difference: the polarity of the gas and the size of the particles. If a gas is composed of polar particles, that means that we have slight charges involved on the ends of those particles, right? Slightly positive ends and slightly negative ends. which means that there's going to be more attractive forces between those particles. More attractive forces means less ideal situation. Therefore, polar gases don't really behave as ideal gases. If you have a gas that's composed of large molecules, then those larger gas particles are going to take up more actual volume. Because of that, gases composed of large particles are less ideal than gases composed of small ones. In the interest of future reference, there is a way we can account for the actual pressure and the actual volume of a gas, even when you consider the size of the particles themselves. In other words, a more real-world situation. We use what's called the van der Waals equation to do this. As you can see, it's a little more complicated. In this equation, we have two extra variables, A and B. These are both dependent upon the type of gas involved. In other words, every gas has its own particular values for A and B. So these are values that you could look up in a reference manual, or they would be given to you in a problem. So you could still solve for a variable in the same way, you just have to do a little more work to get there. Now, how about one problem for homework? I want you to find the molar mass of a vapor that has a density of 0.480 grams per liter at a temperature of 260 degrees Celsius and has a pressure of 0.140 atmospheres. Again, find the molar mass based on those conditions. You might look back previously to see if there was an equation that included density and molar mass. After you're finished, you can put your answer in the LMS. That's all we're doing with this video. Today we began with a discussion of Avogadro's principle, how two different samples of gases can have equal amounts of particles if you have the same temperature, same volume, and same pressure. That led us into a discussion of molar volume, which is 22.4 liters for any gas at standard temperature and pressure. And then we talked about the ideal gas law, how we include the number of moles that previously we didn't. From that, we were able to show how you can determine the molar mass and the density using the ideal gas law. As always, I hope this has been beneficial to you. If I can help you in any other way, please let me know. Until next time, God bless.